Hello everyone, hope all are doing good. Today I'm reflecting one other research paper related to two-player online reinforcement learning fine-tuning for LLMs. Okay, so a large language for large language models, as large language models demonstrate their capability in various fields, their implication to tasks require multi-round interaction has become increasingly popular. These tasks usually have complex dynamics, so supervised fine-tuning on a limited offline dataset does not yield good performance. However, only few works are admitted to directly train the LMs within interactive decision-making environment. We aim to create an effective approach to fine-tuning LMs with online reinforcement learning in this environment. We propose Reflect RL, a two-player system to fine-tune LM using SFT and online LM. Okay, so SFT is supervised fine-tuning, right? So we use negative example generation to enhance the error correction ability of reflection model. Further, we designed a single prompt action enumeration and applied a curriculum learning to allow the policy model to learn more effectively. Empirically, we verify that reflect reinforcement learning outperform SFT and online RL without reflection. Okay, so the main objective of the paper is reflect RL outperform SFT and online RL without reflection. Okay, testing result indicate GPT-2 Excel 1.56 billion parameters fine-tuned with Reflect RL outperform larger open source LLM such as Mistral 7 billion parameter, right? The benchmark dataset and code involved in this work are publicly available. Okay, so LLM I have shown promoting result in problem solving, coding and documenting. While performing this, LLMs exhibit a considerable reasoning, planning, and reflection enabled by prompt and techniques like React, which is already discussed in this paper. Yao, Yetel, Hill, reflection, chain of thoughts, tree of thoughts, and reasoning via planning. Some recent studies, which is in Magister at TL 2033, Mukherjee at TL 2003, Mitra at 2003 also try to improve reasoning ability as small models to match those advanced LLMs, right? The reasoning and reflection skills enable LLMs to act as an agent and interact with the real world environment, including code interpreter, embodied robotics, which is in Sridhar et al. EL 2021, Ahan et al. 2022, Tani et al. 2004 games at Park and many other places. This interaction ability is close tied to reinforcement learning, where agent can learn optimal behavior through trial and error within an environment. Okay. The research is motivated by three testing application domains within the system. I'm learning motivation, page number 1, right? Which include document querying, database searching, and coding, right? In this application, the chatbot needs to navigate in file system to read documents, modify file, and execute code to answer user's question, right? So what chatbot can be doing this is navigate in the file system to read documents, modify files, and execute code to answer users. Central to this task is chatbot ability to autonomously explore within repository using system commands such as ls, sd, src, cat, main.py, similar to the paradigm at Yang et al. 2023. Interactive chatbot system for file system NVIDIA. I mean, I'm not able to pronounce it. NVIDIA 2024 multi-agent framework, VoATL tools selection, and many other industrial applications require interactive decision-making capabilities. Even if LLMs can perform these tasks, they are usually trained heavily with offline supervised learning rather than online training with complex environment. Moreover, the recent studies found that LLMs might not be able to correct themselves without external feedback during interactions. Okay, so what happened, that environment is there. uh, so I'm in page number 2. It is environment, observation, possible action, reflect agent, and reflection, and there is an actions, right? And there is a memory, right? Policy agent is already there. So you are in the middle of the room, you see a cabinet. Okay, reflect agent taking the tomato to the microwave is correct. Next step is to place the tomato, right? Okay, database is already there. Now possible actions is close the microwave, put tomato in microwave, go to the cabinet. Okay, go to the fridge, memory, cook tomato. Task, the main task is here is to cook tomato, right? Act 0, go to the fridge. uh, uh, Abstraction is if it is closed, Open microwave, you see a mug, right? Obstruction. It may be possible that you see mug in a microwave, which is not a possibility, but I mean, it is an obstruction, right? Go to the fridge and it is closed, right? Naturally, I mean, our task is to cook a tomato, right? Policy agent is already defined. Okay, and SFT, supervised fine tuning, is there. We need to fine tune a particular task according to our requirement. So the ultimate aim is to cook a tomato with microwave, right? So we are in the middle of room and you see a cabinet, right? 18 cabinet 3, or maybe there are a lot of cabinet. If we see now we have to put a tomato in the microwave and then cook a tomato, right? Okay. So I mean, solid right represent the forward path for both data generation and inferences. Agent in circular or Lagrange model capable of generating reflection and making decisions. Red dashes line generate the loss and gradient calculation during the training period. The reflection agent is trained with SFT, while the policy agent trained with first with SFT and then with online RLFT. Detailed instructions are for each step in appendix B. The online LLM with human preference promote LM for solving this. Okay, so I mean, what happened that motivated by strength of RL and expensiveness of LLMs, our work aims to fine tune smaller part locally operate LLMs that are capable of decision making and adaptation through reflection, which are essential for domain specific interactive tasks. In this paper, we introduce Reflect RL, a novel approach to dynamically improve LLMs with online reinforcement learning applied with Markov decision processes (MDP) for multi-step decision making. Most of the previous RLM works can be categorized into three classes: treating token generation as reinforcement learning rather than considering embodied tasks, games, or interactive decision making within environment. Using LLMs as an agent to augment policy generation with additional textual information without directly learning from environment, gradient free. Engaging primarily with single step bandit rather than multi step MDBs. Our methods seek to improve multi step decision making in textual environment by interacting techniques from RL and LLMs, enabling LLMs to adapt more efficiently to complex environment. We summarize the key point: reflection. We distilled reflection ability for our domain specific requirement from GPT-4 through supervised learning. The decision LM is frozen and deployed as a reflection model to assist the trainable policy model in decision making. Okay, reflection accelerate training, converges, and improve test performance. The reflection data gathered from GPT-4 is unbalanced, with majority consists of positive near optimal decisions. To balance the data, we generate negative examples by preparing the GPT-4 test trick. Okay, so I mean, there are positive examples and there are negative examples are there, right? And what happened that treating token generation as a reinforcement learning rather than considering embedded task, right? Single prompt action enumeration. We include all possible and valid action into a single prompt, allowing the LM to select the appropriate option using only one token. This approach improves the normalization techniques and various works to generate valid actions and also reduce time complexity. Okay, so I mean, we uncovered the idea of curriculum learning into our pipeline, designing a specific curriculum to guide training by giving extra rewards or scheduling the data order. Okay, so I'm in page number 3 of 21. I'm reading that we introduce Auto Explore, a benchmark inspired by industrial applications, along with benchmark adopted by various works. Okay, same trade with other local LLMs for training or remote LLMs in context inference. Uh, Context inference is naturally we understand, right? So I mean, from positive result and from negative result, they're trying to influence the behavior of chatbot or application, right? And then the benchmark which has already been created. Okay, so I mean, these benchmarks can be reflected on the previous model and how to influence that particular actions or to optimize that particular action so that you know uh, it can be possibly done so by the fine tuning effort or supervised fine tuning effort. The task can be done. Okay, this paper discussing LLMs in section 2 and RL preliminary in section 3. We introduce our proposed reflect RL in section 4 and benchmark in section 5. Okay, large language models and machine translation, text generation showcase their versatility and capability in handling complex linguistic structures. So such agent collaboration can achieve a level of sophistication and efficiency that is difficult to obtain through solo effort. Supervised fine-tuning and reinforcement learning from human feedback are the most commonly used alignment methods for adapting pre-trained LLMs to a specific task. LoRa, this is already a research paper. LoRa, QLoRa, okay, and other parameters efficient fine-tuning PEFT algorithms can facilitate this process. Okay, so I'll summarize in table first discussed in section 1.2. Only a few studies are applied on online RL to LMs for making multiple multi-step decision, which is again a research paper, right? These are two most relevant studies. What preliminary observation? Page number 3 reading that. For a set X, we use this to denote the probability simplex over X, right? So I'm representing this. What is this? Because I'm not able to understand this. Let me the probability simplex, right? Over the set X, the probability simplex is the set of all probability distribution over X. Means that it contains all possible ways to assign non-negative probability to element X, so that probability sums to 1. What probability simplex is saying that you need to assign the all probability related to which are total probability sums to 1, right? Okay, is the set of all vector possibility where each PIs correspond to probability of a event and X, and other probability are non-negative and sums to 1, right? So if the example has 3 elements, the probability of simplex consists of triples P1, P2, 3, which is greater than 0, and P1, P2, 3 equal to 1. Okay, so naturally what happened, it is probability simplex is for the only positive value. Okay, let the tokenizer be fixed throughout the paper. For string, we use S module to denote the number of tokens in S after using this fixed tokenizer. Reinforcement learning problems are usually formulated MDP, Markov decision process. They enable agents to learn optimal behavior through interacting with the environment without human intervention or labeling. A finite horizon MDP is described M, HS, A, mean, T and R. T is a transition state, which we can transition from one state to another state, from one agent to another state, from when the operations are performed from one agent to another agent, and from one state to one action to another state. Then the transition state comes, and the state is already there, action is already there, and reward function is already there, which is represented with R, and that U is inverted U is for the mean, and H is for the state, right? And A is an state action, which is represented by the initial state distribution, which can represent distribution over task. We study deterministic environment in this work as the task in our motivation are deterministic. The transition function maps a state action pair to transition state action, and reward function immediately the reward. Okay, it is like -1 to 1. Given a Markov policy, pi is this, we define its value function and q function, right? So this is this, right? The accepted trend of policy pi is z pi. Okay, then the goal of RL is to find the optimal policy maximization z pi. When modeling an application as an MDP, we may encounter the fact that each state has a separate valid action space. Through we can define A. Okay, as the union could be interactively large, a viable workaround is to define a mapping function such that ES is this. The formulation worked smoothly with our approach named single prompt action enumeration, where A consists of choice such as 0, 1, 2, and function E maps them to detailed action, right? The policy optimal works is J pi, right? Okay, so J power of pi, a policy optimization approach to solve MDP using parameterized policy optimization technique for MDP surround the class of policy gradient. Okay, so it is this. It is inverted this. We'll again put it out this. The expression you have provided for policy gradient methods in reinforcement learning, especially it is an instance of policy gradient theorem, right? Which aims to compute the gradient of the accepted return z pi with respect to the policy parameter theta, right? So let's break it down. It is like the gradient of accepted return with respect to the policy parameter theta, right? So let me see. Okay, H is the time horizon. No step each H is option. So what happened that when the training is happening, time horizon is represented. So from H1 to H indicate the policy is being optimized over all the steps of the episode, right? So expectation over the state. Q is a Q value function, action value function. Okay, time H represents the absolute value and rewarding state from a state action taking action A and then following the policy uh, pi theta for the rest of the episode, right? In simpler terms, what happened that absolutely there is a frame of actions happen that, right? If I go to that refrigerator, the number of refrigerator may be more. Second, the instance of my going is can be recorded, right? So transition state is being automatically being created, right? So what happened that naturally log probability. Naturally what happened that the state can be divided and the transition state can be created. Then the discussion happened with these mathematical notation that how it can be processed. Okay, so I mean okay, so this is acceptation over the state S and action S sampled from policy pi theta at the time of step H, right? So this is how it is a stochastic gradient descent to update theta and improve the policy. Okay, so I'm in page number 3 reading of 21, right? Then we have a token as generation as reinforcement learning work by Ramamurthy and long till 2004 unit 4. Okay, so I'm not opening this, but it is again related to direct instruction, mandate or MDP reflection no, training method RL, LLM as agent. It is again by fellow researcher, MDP, and yes no. Whether there is a reflection, yes or no. For bandit or MDP only. Bandit, for bandit it is already there. MDP no. Yes, SFT RL fine tuning. Sridhar as this research paper. They are all fellow researchers already there. It is Bai, Quang et al., Ziegler et al., Ten et al. This work MDP is there. No, yes. Supervisor RL. Okay, so there are different works already there. Page number 4. I am reading page number 4. RL policy this, S is this, S is the current node. A is dot AIK denote the subsequence. We apply the policy model to multi-step. Okay, so this is lava and actions are already there. Denote action substance. We apply the policy model to multi-step RL task. Okay. Okay. Reinforcement learning, fine tuning. Okay, which is 0 to 1. B is a trajectory. Okay, so especially we first assume access to an independent reflection R to generate reflections. Okay, L reflect is this and work LFT Azure OpenAI Jibdu. Okay, so again this happens, right? This again a very deep in our work. We train local LLMs in SFT. Data collected from Azure OpenAI GPT-4. Okay, R4 is a frozen notice R throughout LFT stage. The policy model is accepted deep. Data contained on the reflection. D is SID RIQ. Okay, loss function can be represented by this. Loss reflect loss policy. Loss at the policy level and loss at the reflection level, right? So this represent by log sigma I1 Li is a reflection action of sigma 1 upon n minus log that state is represent frozen state. Throughout the LFT stage there is a frozen state where we need to understand. Frozen state is also represented in some of the research paper, but it is represented by R cap. Okay, and it is same, right? Rij upon SR Rij j minus 1, right? Same it is. Why am I representing R in this? It is for the reflection model, right? Reflection model is already there when any action is happen. So there is a reflection model. There is a deep annotation of that also, which is there in state and reflection and state is already there in that particular loss gradient function, which I'm reading page number 5 of 21. The equation is R reflect on this, right? So RL50 stage, we first query the reflection of the then complete reflection due to the policy model input. Okay, is this okay? Okay, so RL and SFT is there. Step H, this is government critical for policy model to derive the actions from action. Okay, so training with reflect RL input environment is the best size B, prompting function P, action enumerate function is this, SFT data size N, pretend LM and LM to generate data, MR is the number of update T. Okay, so I mean it is an observation, MRP DS P reflect, AH this, D reflect, and these steps. Look ahead, reflect after wrong action is this, right? D reflect DU negative and this observation, right? So data are exclusively used, according to we used method to generate SFT dataset. Okay, GPT and all this thing. Logically consist trajectory is T, GPT-4. Okay, for we first restore the environment to state as such a manner. We randomly pick an action from the state this. Okay, there is a deep connotation of this also, because they are reflection of the they may be part of the different research paper which has already been done. Okay, so single prompt action in enumeration state dependent, valid action spread over several tokens and has constraint on the token combination. For instance, in LF for the action space can differ across task or locations. Go to cabinet 10 which is contain 4 tokens, while take cabinet 10 is invalid. However, this valid action may become invalid when present in other tasks where cabinet 10 doesn't exist. Okay, so this is how it is. Probability this, normalization over this, calculating this. Okay, so this is action. Suppose order of action is this, we compose this. Okay, curriculum learning is a practical machine learning using a topological ordering of tasks help with the training, right? Benchmark is there, LLF bench. Okay, so what happened that probability is calculated by this normalizing over action state, right? So auto explore, page number 5, reading of 21, right? Benchmark page number 6. Auto explore sandbox for a file protection multi-agent system. Okay, auto explore copilot and auto explore environment label LLMs to interact with file. Right, SFT file, RFT file, SFT plus RLFT, SFT plus RFT is reinforcement learning, right? Okay, so this is how it is. During interaction is this dangerous taxi. During interaction we extend the OpenAI gym taxi environment to introduce a higher level of challenge, thereby creating a danger taxi environment. This game include if the player commits an invalid action such as colliding with a wall or incorrect picking up dropping of passenger at another location. What happens that natural task is that open a refrigerator, open a something and put tomato in that and cook that tomato, right? Microwave. But what happened that in between if something wrong happen, then there is a dangerous taxi or auto explore co-pilot agent, which for every action there is a reward. So the danger taxi is different. We apply to conclude to danger taxi in design pickup curriculum. We assign a positive 20 reward to terminate the environment after drive successfully pick up the passenger. In the drop off stage, the pickup reward is retained, but the driver need to further drop off the passenger destination to sleep. What happened that in danger taxi method they may be defining the policy agent. So what happened that you picked up a passenger, then there is a 20 reward point are given. Then you drop off the passenger, then the full reward is given. In between, if there is anything happen, then there will be no count, right? Then the full reward can be rewarded if there is a drop to the passenger, right? Okay, so this is how it works. Okay, a robot in required to complete a certain task based on description. The bench has got recognition to evaluate LLM agents, right? So experimental. I mean, page number 8 of 21, right? So it is what I mean. Different models are there. 7 billion parameter model, open source 7 billion model, auto explore depth one, and same. I mean, same. These are same. Okay, reflection. Okay, okay. RL methods are there. Okay, okay. So I mean, page number 9 of 21. Okay. For dangerous practice, we're using the same policy after reflection. We use a reflection model to GPT-2. Okay. So and it has different percentages also, 55%, 58%, 64%, right? Okay, okay. The primary goal of the study to create an efficient online RL pipeline for LLMs to perform multi-step problem solving. Building on this foundation, future research direction may explore the scalability of Reflect RL to develop a large language models, enabling them to adapt to a previously unseen environment without of domain generalization capability. The two-player designer framework may naturally be extended to the other multi-agent settings when language models can show their strength, and another future direction is to train the reflection model in LFT stage as we freeze it because of the inference of the policy model. Okay, so I mean naturally when I'm in page number 17, what happened that I mean pick up the passenger and dropping of the passenger and the reward point in between the process, right? Same like we use Nevada, RTX 4090 and RTX 10 Tesla for the train, and Tesla A40 for training and evaluation of proposed reflective RL method. PyTorch and Hugging Face Autogen are also used throughout the project. So I mean these libraries also can be used throughout the project. All the experiments share the set of parameters. For Auto Explorer, it takes around 30 seconds per iteration during the setting of Horizon Edge 15. I mean for 30 seconds per iteration. When one iteration happens, they taken a 30 seconds, right? Edge 15 is in a pickup and 60 seconds per iteration throughout the setting of Horizon Edge, 30 in a drop off, right? So in for LF it take 90 seconds per iteration for setting Horizon Edge equal to 15, right? Okay, so I mean this is what it is. Okay. So I mean it is an observation. I'm jumped to page number 17. Okay. Uh, Earlier I have already discussed the algorithms with training with reflect RL. I mean there may be a separate video needed for reflection of these algorithms only. Okay. So concurrent learning is there. We have pick up and drop and there, which is already there. Auto explore, dangerous taxi pick up and drop, right? So I mean in SFT, RLFT, auto explore. When auto explore there and dangerous taxi and ALF world. I mean ALF world is conclusion of that. Maybe the part of that maybe an another you can say what discipline which can be arises, right? So I mean auto explore depth 1, depth 2, and this can be done, right? Okay. So I mean this in ALF world, a multi-turn platform tailored for simulating household tasks by converting the graphical representation of house into descriptive language. Okay, I mean in ALF world there is an house representation. In dangerous taxi we already reflect. Okay, in auto explore, I mean, something is happening in auto. This benchmark contains three component: auto explore and for file protection, multi-agent system. For auto explore sandbox is for file protection. Auto explore copilot for interactive decision making, and a labeled dataset for performance assessment, right? So I mean I will reflect on this also, because for house setting they are doing different. I mean for house setting it may be different environment, state action and representation. But compressive autonomous exploration consists of three components: auto explore sandbox, auto explore copilot, and labeled dataset for performance assessment, right? A labeled dataset is essential for evaluating the performance of autonomous exploration. The dataset contains ground truth information against which is the Model exploration behavior can be compared. Measuring the performance of data, we can continually assess how well the exploration strategy works, possibly using matrices this coverage, efficiency, and decision accuracy. Data flow environment mentioned is a key part of a system, allowing language model to interact with the files. The interaction capability will enable LLMs to make decisions based on file contents, navigating directory, reading or modifying files, and take action based on the data encountered during exploration. Right. Effectiveness of autonomous exploration models, providing a secure, collaborative, and measurable environment for experimentation and evaluation. Okay, so this I have already done, right? SFT plus RLT, SFT plus RLT, work of reflection, work of negative, reflect RL, right? Okay, so this I have already done, right? Already done the explanation of it. Auto explore by each step, agent receive -1 reward as the cost of time. After 15 steps, auto explore copilot is also representation of auto explore copilot is also in some setting, right? Because reinforcement learning framework where a multi agent system to locate the correct file, right? Naturally, we need to correct for auto explore copilot is the reward point for explore the correct file, right? Per step time cost negative reward, right? For every step the agent takes, it receive a reward of -1. This is when the cost of time, encouraging the agent to make an efficient decision, find the correct file as quickly as possible. If the agent takes too long to explore it, will account a negative reward, slower inefficient exploration. If that particular agent can able to reflect particular action on particular time period, then there is a reward. Otherwise, there is a negative reward -1. Episode termination: the agent can terminate the episode in 2 ways after 15 steps. If agent takes 15 steps without identifying the correct file, the episode automatically ends. The agent has the option to terminate the episode earlier if it believes it has to identify the correct file. If the agent correctly identifies the target file, it is a 15 award plus 15 reward, which is significant positive reinforcement, encouraging. If correct file is identification, plus 15 is there, right? After 15 steps. Okay, so one episode is ended when the file is find out, right? If the agent fails to identify the correct file or wrong choice, it is a -15 reward, right? After 15 steps, if the agent not able to find the correct file, then it's -15. First step reward is -1, correct file identification plus 15, incorrect file identification -15. Penalty for failures. Okay, so this way it is happening in this way, right? Dangerous taxi. Okay. This is this way. So auto export depth is this. You need to correct file matter, and ELF world is simply to find microwave and in kitchen setting. We are doing this experimenting in kitchen setting, right? We need to fetch a tomato and cook a tomato, right? Okay, so this is RL based observations. You can read this research paper to know more about that. Okay, I will jump to the page number mathematics information policy, proximal policy optimization is also there. Okay, so the reflection, I will leave this 26, but I'm just to page number 14 of 21, right? So what it says: you are in the middle of the room, you see a cabinet 18, cabinet 3A, GPT-4 reflector. Taking the tomato to the microwave is correct. Next step is to place the tomato, right? Database is comes, right? Action 2. Now what happens at first action is that you are standing in the middle of the room and you see a cabinet, right? This is observation, right? Second, taking the tomato to the microwave is correct. Next step is to place the tomato. You have to take the tomato from the microwave and place the tomato. Second is close the microwave, put the tomato in the microwave and go to the cabinet. Okay. Go to the fridge, it is closed. Open the microwave, you see a mug, right? Memory, it is a memory task is to cook tomato, right? Abstraction is this side. GPT-4 policy is same. That taking the tomato to the microwave is correct. Next step is to place the tomato. Taking the tomato to the microwave, first there is a tomato in your hand. Observation. You have to take the tomato to the microwave. Next to place the tomato. Okay, and then close the microwave, put the tomato in microwave, go to the cabinet. Okay, close microwave, put the tomato in microwave, go to the cabinet. So once, okay, so possible actions, naturally it is repetitive in the nature. Okay, you are in the middle of the room, you see cabinet A3 reflective agent. So we have created a same reflective RL data generation agent. Okay, when the two action is performed, right? So what happened? The reflective agent can do the same task to microwave. Next is to place the tomato. Okay, policy agent is uh, pi theta. Okay, reflective agent, pipeline of the reflective agent are acceptations. So what happened that in reflective agent, reflect agent, which is represented by this, there is a loss gradient formation which is already defined by self reflection, right? Action is already happened. The reflection of action is already happened. I'm in page number 14, reading of 21, reading the same. The pipeline of reflect RF stage. Okay, so I mean, when there is a policy gradient state and action, we define this as a upon s, right? Reward function is already there when any one of the reward comes, right? So uh, I mean, what happened that one action is there, we create a replicate out of that action. Then there is another action, pipeline of reflect RL RFT stage, right? So so this, I mean, okay, this the expression you provided is this: key component policy gradient method reinforcement learning, action value function, log probability. Okay, interruption is this. In policy gradient methods, this expression is used to calculate the direction and magnitude of the update to the policy parameter is q. So it indicates that when action is taken, yield a return, high return, QSA is high, and gradient is this, will have a positive effect on policy update. The goal is to increase the probability of taking such action in future. Okay. Okay, reinforce. I mean, reinforce in about the expression is operated into overall gradient of experiment and this, right? Okay, so I mean, the form the basis for updating the policy matters and algorithm reinforce on other critical methods, right? So I mean, it is a reinforcement action. What happened that its action by itself is self-reflecting, is state in action. Okay, it is a reward in this. Okay, so it is the best language model is this. Okay, auto explore sandbox. Okay, uh, Copilot is an agent between language models. Auto explore Copilot and and these all things, right? So I mean, other benchmark like I mean, I'm reading page number 16 of 21. Your helpful assistant, you need to generate a sequence of system commands to identify the correct file. During interaction, you can only output a single choice number as response. Here is p negative. Last command opens the wrong folder or file, which is the suboptimal move. Given the reason why the folder file is incorrect and plan what to do the next using 50 words. Don't give the choice yet. Okay, so dangerous taxi assumption is this. Right, I mean, you need to reflection on your action. What is the consequence of your previous action? How is your previous action? What's your next action? You want to take it possible? Why? I might you give some spoiler information and optimal action for cheating, but you should not mention that you have seen any spoiler. Okay, don't use any words reflected to optimal in your reflection. Keep your reflection concise within 100 words. For instance, because I task is the found is. So what happened that reflection must be with 100 words or less than 100 words, because the task is 2. I found out p negative, the previous action might be contain some mistake. Okay, ALF world and text world use MIT license. Okay, same system as a p negative use dangerous taxi. Train batch size is 1 of 409, 09, 2 of 160A40. Okay, so I mean. So I mean, this happens. You're in the middle of room looking around you. You see cabinet fridge, and your task is to put a tomato in microwave. Begin by searching cabinet fridges to find a tomato. Then place in it is a microwave. Check cabinet. The most common places to find a tomato is in the cabinet or fridge. But sometimes cabinet isn't relevant, right? I mean, it may be where the tomato is already been kept. So you need to go to cabinet 1, go to the cabinet 10, go to the fridge 1, and go to the pick the tomato from fridge 1. Go to the cabinet. Which cabinet? It may be 1 to 10, right? It may be fridge, with type of fridge, maybe there is two fridge. So I mean there is an action list of this. Okay. So look, we are in the middle of looking around. You see cabinet 20, asked to put a tomato in microwave. Okay. Go to the fridge. You arrive at location for 24. The fridge one is closed. The initial action of going to the fridge aligns well with the task, as tomatoes are typically stored in the fridge. To progress, the next logical action would be open the fridge to search for a tomato. Examine fridge 1, go to cabinet and open fridge 1 action. You are in the observation of the middle room, looking around you, you see a cabinet 20. Okay, take the fridge. Then again, you open the fridge 1, the fridge 1 is open. You see egg 1, pot 2, pot 1, tomato 1, tomato 2. My listening action as you located and open the fridge to find the tomato necessary for my task. My task is represent the tomato in fridge. There may be egg, pot, or maybe anything else, right? Then process the put in the microwave to complete the task. Close the fridge. Take the tomato from the fridge. You are in the middle of your room, looking around you. You see cabinet 20 microwave. You task it to put the tomato in microwave. Is the previous path. Take a tomato 2 from the fridge. Observation: you move a tomato 2 from the fridge. 1. The action taken so far have been effectively brought the tomato into my hand, which is in alignment with the first part of a given task. The next step is to navigate the microwave and complete the operations to place the tomato inside it to fulfill the objective. Close fridge 1. Go to the microwave 1. Okay. You are in the middle of room. Step 0 to 3. You task to put a tomato in microwave. Arrive at location 22. The microwave is closed. Microwave 1 is closed. Action takes a while. Successfully identify and identify the tomato from the fridge. Progressively towards the task goal. Next step should be open the microwave and put the tomato inside to complete the task. Okay, so actions with every step is already counted, right? And every action is counted. Examine microwave for action or open microwave first. Okay. So you're in the middle of room again. Our observation. Put a tomato in microwave. On reflection, successfully walking the director from the which was correct step toward completing the task. However, on our side occurred not moving mug from the microwave before attempting to place the tomato inside. In microwave there is already mug, right? So the next action should be to put the tomato in the microwave, which completes the task at hand, right? Close microwave 1. Put the tomato in on microwave for action. What is the reason for planned domain name change for website? Current working directory, files under work. In auto. It's the next form of action. Okay. So it is like, what is the reason for planned domain name change for website? Okay. So this is how it is. I have read it that okay. Last, what is the reason for planned domain name change for the website? Files under current working directory, and we need to check the files under current working directory. If that is there, we can reflect that, and which file is there. Okay. So thorough